Okay, so what I want to go over in the first page is that just like acid-base chemistry, we gave you two different types of definitions. Like the Arrhenius definition was the original definition dealing with hydronium ion in water, but then the Bronsted-Lowry definition was a more recent one, so it expanded. It was a better definition. Oxidation reduction has a similar thing, where we knew of oxidation a long time ago. And what oxidation means today is an element is losing electrons or electron. You guys don't actually have to figure out how many electrons are lost in any of these equations. You just have to identify whether or not it is losing. But that is the skill that you would have to know if you took future chemistry courses. The old definition was anything that gained an oxygen in a chemical reaction, or it lost a hydrogen. Now, I'm not going to ask that you know the old definition. However, you better know lose electrons for oxidize. There's a reason why I'm showing you the old definition. I'm going to go over that in a second. Reduction is an element gaining electrons. And this is where students don't like that term. To reduce means gaining electrons? I don't like it. Those words don't really match together. But the reason why that term is there is the original definition of reduction was based off a compound losing oxygen off of it. So you're reducing the number of oxygens. And as you'll see in a little bit when we do a reaction with this, there's another good reason why it's called reduction, even though reduction is gaining electrons. So what you need to know on this slide is that oxidation is losing electrons, reduction is gaining electrons. Again, we are not huge advocates of giving you terms and definitions throughout chemistry. However, these are two terms that you got to know. Just like you have to know molarity is the concentration of a solution, you need to know these two terms. But this is where I give you a gift, Kobe. Are you ready? This is me giving you a way to remember these two terms and what they mean. Are you sure you're ready? Yes. This might be one of the very few things you actually remember from chemistry in years to come. Kind of like when I ask Noah what's new. He knows c over lambda, speed of light over the wavelength is the frequency. Leo goes grr. Leo's a line in this case, Alyssa. Even my 1-year-old, I can ask her, Josie, what sound does a line make? She'll say, grr. She's got her sound. She knows a pretty good sheep of a ba, a horse is a neigh. Her duck quack isn't very good. She doesn't have the quack part out. Lose electrons, oxidized. Gain electrons, reduced. You know how some people will write that molarity triangle at the top of a test to remind themselves I can solve for any variable that I want to within molarity calculation? People will write this on the top of their test as well to remind themselves, lose electrons, oxidize. Gain electrons, reduce. Plus, Ava, if you get this wrong as I'm walking by, I will just grr right in your face. Okay, now, the reason why it's called an oxidation reduction reaction, or redox for short, is because both things have to occur. That's what my bottom point is saying here. You can't have a chemical reaction where something just gains electrons. Because if that was the case, where did it gain electrons from? You can't just have a chemical reaction where something loses electrons. Elements don't just decide, I've had enough of these electrons, let's just get rid of them. There's a give and a take. And our goal today is to look at a chemical reaction using oxidation numbers and determine what element lost electrons, what element gained electrons. By doing so, we learn more about the mechanism of the reaction. By doing so, we laid the groundwork of applications of redox, which in chemistry there are a few. Again, I mentioned a couple at the beginning of class of electrochemistry and cellular respiration. We talked about AP Bio type stuff. So our goal in these next 2 days is to write chemical reactions just like we've been doing for the past month. Assign oxidation numbers just like you did in the past 15 minutes. And then use Leo goes guard to determine, hey, that thing was oxidized, that thing was reduced. A couple more slides to go. Okay. Don't know if you have to write all this down first off. You might just want to leave this blank because the definitions are on the previous slide. We, again, use oxidation numbers start to finish. So if we look at the oxidation number of every element to start and after, we can determine if it was oxidized or reduced. And again, the last thing I mentioned on the slide is if a reaction is a redox reaction, it's due to a change in the oxidation number. I will say, however, that not every reaction is a redox reaction. And sometimes that's all you have to prove as well. Kind of like when you did double displacement things, sometimes you want to create a precipitate, so that reaction didn't occur. Well, not every reaction is actually redox, even if it does occur. So this slide, again, probably not important that we jot down. This is more for me to remind myself to explain it to you. This is what we're doing today. This is what you're going to be practicing next time when I'm not here. Write a reaction, give oxidation numbers, and then from there, determine, okay, what was oxidized, what was reduced. My last slide is a sample problem. Once we get through with that, then you guys are going to work on this with the handout you picked up on the way in for the rest of class. It gives you practice in writing reactions and then doing the rest from there. Okay, here's the reaction we're going to look at. Do we remember what type of reaction this was from last unit? Single displacement. Again, we're not going to throw new stuff at you here, folks. We're going to show you reactions you already know, but now we are classifying them differently. What I'd like you to do is write this reaction down. Again, I apologize for no phase notations. The lone elements would be solid, the compounds would be aqueous. I want you to take a minute to assign oxidation numbers for the elements, start and finish. That's the first thing we have to do in order to determine if there was a change that occurred. As you're finishing this up, not everything has to change. Just like in a double displacement reaction, you're going to have spectator ions, things that are the same start to finish. You're going to have a spectator in this as well. That SO4 to start with and end with doesn't change. The oxygen's a -2, the sulfur's a +6, right? So sulfate is kind of a spectator in this. The change, the zinc started as a 0. And again, you probably wrote it right up above. I didn't know how to do that with this, so I just wrote it underneath. But when it became zinc sulfate, it was a +2. Now, if you're not sure, how did I figure out it was a +2? Sulfate polyatomic ion is a -2 charge. The zinc must be a +2 to balance it out. In copper 2 sulfate, copper starts as a +2, and when it's by itself, it's a 0. And again, the S's and the O's stayed the same, but we have a change. What you're expected to do is to write an equation, assign oxidation numbers, and then be able to identify that the zinc lost electrons. Electrons are negative particles, which means when you lose a negative, you become more positive. Copper gained electrons. Therefore, it is reduced. Lose electrons oxidized, Leo. Gain electrons reduced, Ger. Now, the very last thing I want to leave you with is students are good at writing equations. Students are good at assigning oxidation numbers. Students are good at remembering Leo goes Ger. However, it's very common for them to mix up what was oxidized and what was reduced, because students forget that electrons are negative particles. And if you lose a negative, you become more positive, just like the zinc did. If you gain a negative, you become less positive, like the copper did. So there's one last thing to remind you about, other than Leo goes Gur, and why it's called oxidized and reduced. If the oxidation number gets smaller, start to finish, that number was reduced. That element was reduced. If the oxidation number gets bigger, start to finish, it was oxidized. When zinc goes from a 0 to a +2, the oxidation number increased for zinc. That means zinc was oxidized. When copper starts as a 2 and goes down to a 0, its number was reduced. There can be negative values involved with this as well for oxidation numbers, so be careful of that. However, that's the part on the bottom that's helpful for students. To identify oxidized versus reduced, look at the numbers. If they got bigger, oxidized. If they got smaller, reduced. And then if I ask you what does that mean, go back to Leo goes Gur. Well, oxidized means you lost electrons. Reduced means you gained electrons.